So the process we've been doing so far, where we're adding up a whole bunch of rectangles, is called Riemann sums. And this helps us approximate the areas under a curve. Thus far, we've had functions where the area between the curve and the x-axis, because that's what we're really meaning when we say the area under the curve, is that space between the curve and the x-axis. So far, our functions have all been above the x-axis. Well, that will start to change now. Any area that's above the x-axis is considered positive area, whereas any area that is below the x-axis is considered negative area. So in this section, if we had a curve that had three parts, A, B, and C there, the A would be positive area, then we would subtract off our area for B, and then add on our area for C. Adding all of our rectangles approximates the area under the curve. We will start to express the exact area under the curve with what is called an integral. If we make our number of rectangles go towards infinity, that's that limit as n goes to infinity, n is our number of rectangles, those rectangles are going to get so tiny that our approximation is going to become better and better and better, and it will approach what the actual area is under the curve. So remember, the definition of what a limit is what you're approaching. So that area that we're approaching, as our number of rectangles becomes huge, will be our area underneath the curve. We will use this with what's called integral notation. And we're going to use this function we see here, and we'll do it from 0 to pi. So in general, the limit and the summation is going to get replaced by an integral sign. Okay, and on the right side of the equal sign there, you see our integral. Then we'll have our function where we'll have x's instead of xi's. And then delta x gets replaced by dx. And the dx, remember, is telling us what variable we're doing it with respect to. So in our particular case, if we're going from 0 to pi, we would have the integral. We would have x cubed plus x sine x dx. And because we're going from 0 to pi, we would put 0 on the bottom, pi on the top. So where your interval starts goes on the bottom of the integral symbol. Where the interval ends goes on the top of the integral symbol. We've got our function f of x, and then dx is telling us our variable that we're doing things with respect to. And this is an expression that represents the exact area under our curve, because it's our limit as our number of rectangles is going towards infinity. So we will be working with some formulas that we saw in the previous video. Here's the first one when we just have I. We'll use these sum formulas today to evaluate a integral later in the video. Here are our other ones. This was our one where we're adding squares and adding cubes. Again, we saw those in a previous video. And then we have our one with our constant. And then a couple properties here. So if you have a constant times something and you're doing the summation of it, the constant can be pulled out in front of the summation. Also, if you're adding or subtracting two things inside your summation, you can do their summation separately. So next example we're going to do is very similar to what we did in class. We're going to do it with our rectangles. So we want to evaluate the sum of f of x. We're going to do right-hand endpoints. We're going from 0 to 3, and we're going to do 6 rectangles. So first we have to find our width. So we'll do b minus a over n. So we'll do 3 minus 0 over 6. That'll give us that our width of each rectangle is a half. So our intervals, we're going to go 0 to a half. We'll go 1/2 to 1. We'll go 1 to 1.5. We'll go 1.5 to 2. Okay, in brackets, parentheses, doesn't really matter for this. We're just listing them out so it's easier for us to pick out. So we have 2, 2.5, and then we have 2.53. The reason I like to do this is, well, we're working with right-hand endpoints, so just take all the things in the right-hand ends of the intervals. So we always do our width, and then f of each of our right-hand endpoints added up. So we'll have f of 1/2, which we'll put in as 0.5, plus f of 1, plus f of 1.5, plus f of 2, plus f of 2.5, plus f of 3. So listing out your intervals like that can make it easier to pick what our values are that we're plugging into our function. So remember, the easy way to do this is in a graphs page, sub in f of x equals x cubed minus 6x, say in like f of 1, and then in the calculator page, you'll just do 1/2 times f1 of 0.5 plus f1 of 0.1 plus f1 of 1.5 and so forth. And when you do that, for f of 0.5, we're going to get negative 2.875. Now notice if we're getting negative area for that, that means that part of the graph must have been under the x-axis. We'll get negative 5, negative 5.625. We'll get minus 4. Then next we get plus 0.625. That must mean our graph is now above the x-axis. So we have positive area. Then we have plus 9. And if we punch that all in, we get negative 3.9375. And this is an estimate of our area between the graph and the x-axis. Now, because it's negative, that means we must have more area underneath the x-axis than we have above the x-axis. And here's a picture of what we see. So we have 4 of those rectangles with their right-hand reference points. We're below the x-axis, and then 2 of them were above. All right, we're going to look at this definite integral, and we're going to evaluate it from 0 to 3. Well, to do that, we're going to turn it back into the limit notation we saw earlier in the video. So this is the same as saying the limit as n approaches infinity of our summation of I equals 1 to n. Now here we have to have whatever our width would be, because we're going to add up all of our rectangles. Well, if we do b minus a, it would be 3 minus 0 over n, which would give us 3 over n. So essentially what we're doing is we're taking our width that normally goes out front, and we're just adding all of our, basically our reference points. And then the summation is essentially adding each of those up. Well, to see what we should sub in for x, let's go off to the side. Our interval should start at 0. And then our next one will be 3n. And because we're going to infinity, it doesn't really matter where you think of them as being, as far as like right-hand endpoints, left-hand endpoints, so forth. So let's say we were doing left-hand endpoints. So let's do 0, 3 over n. And that's because our width is 3 over n. Well, then our next one must be 3 over n, and then whatever twice that is. So it would be 2 times 3 over n. Okay, I'm purposely listing it like that, rather than writing 6 over n. So then we'd have 2 times 3 over n, and 3 times 3 over n. And then we would have 3 times 3 over n, and we would have 4 times 3 over n. And this would keep going. So our first reference point came out of here, or sorry, our 0th reference point. Our first came out of here. Our second came out of here. Our third came out of there. So let's imagine we had our ith reference point. So this would be xi. Well, notice the first one, this was really 3 times 1. The second one, this was really 3 times 2. Then we had 3 times 3. So we would really have 3n times I for this next one here. So that is the x value that we would be subbing in. Again, what that does is it represents some random point that we are picking in our interval. Okay, because we want it to be some general thing, and if we basically just write them out and follow the pattern, that can tell us what we are working with. So we are going to have 3i over n cubed minus 6 times 3i over n. And what that is, we're subbing in for x what that random reference point is for our ith rectangle. Okay, the ith one is just saying someone way down the line. Well, now we're going to use our summation rules. So we're going to do the limit as n approaches infinity. Well, n is some constant number. It's our number of rectangles, so 3 over n is a constant. So we can pull that out in front of our summation. Then we'll have the summation of I equals 1 to n. If we cube both those things, 3 cubed is 27. So we'll have 27, we'll have I cubed, and we'll have n cubed. And by our summation rules, we can do our subtraction of our summation separately. So we'll do a summation. We'll subtract the summation of I equals 1 to n, and we'll have 18i over n when we multiply those together. Well, remember, our summation, we're only subbing in for the i's. So our numbers and our n's are actually constants. So we can rewrite this as the limit as n approaches infinity of 3 over n, parentheses. We can pull out the 27 over n cubed, and then we'll leave our summation as I equals 1 to n of I cubed, minus, we can pull out, that was a terrible minus, we'll do minus, we'll have 18 over n, and then we'll have our summation of I equals 1 to n of I. And the whole purpose is to write this in a way where we can use our summation formulas. So I'll rewrite this. We've got the limit now as n approaches infinity. We've got 3 over n times 27 over n cubed. And then we've got a formula for our summation of I cubed. So this is just going to become n times n plus 1 over 6, or sorry, over 2. The 6 is for the squared one. And then that's all squared, minus 18 over n. And then we'll have n times n plus 1 over 2. That's our summation for just I. And those, again, are coming from our formulas we saw in the previous video and earlier in this video. And we need one more parenthesis there. Okay, so that takes care of our summation, and now we just have a limit that we have to neaten up. Well, first thing I'm going to do is distribute the 3 over n to each of those. So this will become the limit as n approaches infinity of 81 over n to the 4th. I'm going to distribute the n and make this n squared plus n over 2, all squared. Again, we distributed the 3 over n, so this becomes minus 54 over n squared. And this one, I'm going to leave as n times n plus 1, and you'll see why shortly, all over 2. Well, this is where we have to get a little bit clever. I want to take that n to the 4th and put it inside the thing being squared, and I want to take that 2 in the denominator and pull it out. So this is going to become limit as n approaches infinity. If I take this 2 and bring it out, it's going to be a 4. And then we'll keep the 81 on top. Okay, and the 4 is coming from 2 squared is 4. Now I want to put inside these brackets, I want to put this n to the 4th. Well, we want it to still just have the value of n to the 4th. And this whole bracket's getting squared. Well, that means we would have to put it as an n squared inside. So all we did is we swapped where the 2 and the n to the 4th were, but because 1 was getting squared, we had to square the 2, and basically you're taking the square root of n to the 4th, so it still has the same value, because n squared squared will still be n to the 4th. And we're going to do a similar idea here with the n squared and 2. So we'll have 54 over 2. We'll have n times n plus 1 all over n squared. And basically, we're just going to keep working to neaten this up. So this will now be the limit as n approaches infinity of 81 over 4. If we divide these both by n squared, we get 1 plus 1 over n to the second. This will be minus 54 over 2. And of course, you could divide that if you wanted. Now, one of the n's is going to cancel out here. And then the remaining one will divide the n plus 1. So we'll be left with 1 plus 1 over n. And now we're going to evaluate our limit. As n goes to infinity, the denominator will get huge, meaning this fraction will go to 0. So we'll just have 81 over 4 times 1 squared. So if 81 over 4 times 1 squared minus 54 over 2, again, infinity, as the bottom goes to infinity, that fraction will go to 0, so we'll just have 1. Okay, and that takes care of the limit. So now we can just sub this all in, and this will end up giving us negative 6.75. And what that is the exact value of the area under our curve from 0 to 3 for x cubed minus 6x. And because it's negative, that means there must be more area underneath the x-axis than there is above the x-axis. So these are very challenging. We're going to keep working in class, working with our summation formulas with different things, and we'll continue to practice those in the days to come. That's all for today's video. We'll see you next class period.